Hello, my name is Alyssa, and I'm a graduate student at the University of California, Irvine in the Carlton Research Group. And I'm very excited to talk to you about my project concerning meteorology and dust, uncertainty in ambient aerosol liquid water prediction. Aerosol liquid water, or ALW, is a ubiquitous component of aerosol mass around the world. ALW has effects on a variety of atmospheric conditions, including on visibility and on aerosol optical depth, or AOD. When we examine AOD patterns over the contiguous United States, we see some very interesting patterns. The top right-hand figure shows the seasonal difference in AOD, with summer minus winter values. In this, we can see that there is a summertime enhancement of AOD over the southeastern United States. And this enhancement cannot be explained by surface measurements of fine particle mass. The bottom figure shows seasonal difference in surface level aerosol liquid water, again, summer minus winter values. Here, we can see that aerosol liquid water content shows enhancement following the same spatial patterns as aerosol optical depth, which means that ALW offers a plausible explanation to reconcile satellite AOD with surface measurements. Now, despite its abundance and importance, ALW is not routinely measured at air quality monitoring stations, which means we rely on modeling to estimate ambient ALW. ALW is estimated as a function of relative humidity, temperature, particle concentration, and particle chemical composition. Now, while this seems straightforward, this estimate faces two major forms of uncertainties. First, measurements of chemical data and meteorology are not often co-located, which means that we need to use reanalysis datasets to retrieve inputs for temperature and relative humidity. Two common models used over the contiguous United States are the North American Regional Reanalysis Model, or the NAR, and the European Center for Medium Range Weather Forecast, or ECMWF model. Second, both aerosol optical depth retrievals and ALW estimates are sensitive to dust species, where dust hygroscopicity and reflectance create uncertainties in remote sensing and ALW estimates. Considering these factors, it is imperative that we perform a comprehensive analysis of these differing data products to ensure that we have adequate predictive skill of ALW and its effects on atmospheric conditions. For this analysis, we look at two different regions. First, the Southeast US, which represents a humid region, and second, the Great Basin, which represents an arid or dry region. To calculate ALW, we retrieve meteorological inputs of temperature and relative humidity from either the NAR or ECMWF model. Neither of these models gives just relative humidity outright. From the NAR, we retrieve values for specific humidity and then convert those into relative humidity. And for the ECMWF, we can either retrieve values for specific humidity or dew point to convert into RH. To ensure that the findings for both the dew point and specific humidity conversions is consistent for the ECMWF model, both data products will be evaluated here. We then pair this meteorological data with chemical data retrieved from the improved network, which provides 24-hour average chemical data every 3 days. In the case without dust, we use just nitrate and sulfate inputs. When we include dust species, we include sulfate, nitrate, calcium, potassium, magnesium, sodium, and chloride. We then use the thermodynamic equilibrium model, isoropia, from which we can then retrieve values for aerosol liquid water. Since we're interested in comparing the differences between these various inputs, we will use a two-sided Mann-Whitney U-test to determine the statistical significance of our results. Starting in the Southeast, or the humid region, I first want to compare the differences between the NAR and ECMWF meteorological models. The x-axis shows data from the NAR, and the y-axis shows data from the ECMWF. The black line is added just for reference and represents what a one-to-one relationship would look like. When we compare the predicted temperature between the two models, we can see that on average, the NAR model predicts a higher temperature than the ECMWF. When we compare relative humidity, we can see that these models produce substantially different values from one another for this variable. And in turn, when we compare the predicted ALW content, we can see that the NAR and ECMWF predict considerably different values from one another for ALW. And this indicates that differences in temperature and RH inputs between these two models will change our predictions of ALW in this region. To examine this a little further, we can use violin plots. Each violin shows the distribution of the data, where the widest part of the violin represents the value at which we have the most observations, and the thinnest part of the violin is where there are the fewest observations. For added clarity, I've also overlaid a traditional box plot over each violin to help better visualize the median and quartile values. When we compare the NAR and ECMWF, we can see that these two models produce very different distributions from one another, with the ECMWF generally predicting a lesser amount of ALW than the NAR. These differences are statistically significant for both the dew point and specific humidity RH conversions. With these plots, we can also examine the effects of dust species with the ECMWF model. In this region, we can see that the inclusion of dust does not change the overall distribution of the data very much. However, it does decrease the amount of predicted aerosol liquid water. These differences are again significant for both methods of relative humidity conversion. This demonstrates that both the uncertainties due to dust and meteorology are significant in this region, and these uncertainties are similar in magnitude to one another. Finally, we can compare the specific humidity and dew point conversions to one another. So each conversion does slightly change our predicted aerosol liquid water content. These differences are not statistically significant, which shows that either data products can be used for these calculations. Next, we'll move on to the Great Basin or the arid region. Again, NAR data is displayed on the x-axis and ECMWF data is shown on the y. Here we can see a profound difference in the temperatures predicted by the models, where the NAR is running substantially hotter than the ECMWF. Similarly, when we look at relative humidity, we can see that on average, the ECMWF predicts a higher amount of relative humidity than the NAR. And finally, when we compare predicted aerosol liquid water in this region, we can see that on average, the ECMWF predicts a greater amount of aerosol liquid water than the NAR. And this shows that in an arid region, the differences between these meteorological models is likely to increase our predicted aerosol liquid water. Again, we can examine this more closely using violin plots. Here, we can see that the NAR and ECMWF models, again, have largely different distributions from one another, with the ECMWF model predicting a higher median value of ALW than the NAR. These differences are statistically significant. When we examine the effects of dust in this region, we see a really large shift in the distribution of the data, where the inclusion of dust greatly reduces our predicted aerosol liquid water content. This difference is highly significant, with a p-value very close to 0. This indicates that both meteorology and the inclusion of dust significantly changes our predicted aerosol liquid water in this region. However, the impact of dust is much greater than that from meteorology. In conclusion, there are significant uncertainties associated both with meteorological models and the inclusion of dust species in the prediction of ambient aerosol liquid water. There is no significant difference, however, between the dew point and specific humidity RH conversions when using the ECMWF model. In the Southeast US, or a humid region, the uncertainties between meteorology and dust are similar in magnitude. But in the Great Basin, or the arid region, the uncertainties due to dust are much greater than those due to meteorology. For future work on this project, we will be expanding this analysis across the contiguous United States to ensure that these findings are robust. We will also be comparing our results from this project to in-situ measurements of ALW from the 2013 SOAS field campaign to ensure that our values are accurate to real-world measurements. Further, we would like to investigate the effects these uncertainties impose on related properties, such as light extinction and aerosol optical depth. With that, I would like to acknowledge and thank everyone who has helped with this project thus far. I will be available to chat on Monday, October 10th from 6 to 7:30 p.m. EDT, or you can send any questions you may have to the listed email, or scan the QR code to get a direct link to my email. Thank you so much for taking the time to listen to my presentation.